Okay. Hey, everybody.
Hi.
Office hours are live. What questions do we have?
Hold on, I have this set up. Oh, so I had a question on the, do you call it oxo-acids, or I also saw oxy-acids?
Ooh.
Does it matter?
Okay, so those pretty much mean the same thing. Oxygen acids, I call them oxo-acids for short. So that's just a definitional thing. Oxy-acids are probably also oxygen acids.
Okay, so after yesterday, I had a question on the homework on 6E and F.
Okay.
So when I saw H2SO4 and then H2SeO4, I know those are oxo-acids, right? Are CCl3CO2H and CH3CO2H, are those also oxo?
Ooh, so let's get those. That's CCl3.
CCl3CO2H.
And
CH3CO2H.
So there's a more suggestive way that we can write both of these. We can write this one as, let's do the second one first. We'll recognize it, hopefully. CH3COOH.
Oh, yeah.
Right? They just combine the O's in the problem. I don't know why. But there's a lot of different ways we can write down structures or molecular formulas. And this one is suggestive of the structure. We can pretty clearly say that's going to be like that. Mm-hmm. Right? We've got our hydrogens all over this for a methyl group. Then we've got a carboxylic group over here. And can we point out which one is going to be the acidic proton? That's the acidic proton. If that's the acidic proton, notice since it's directly attached to the oxygen, that's going to make it an oxo-acid. This second one is actually going to be the exact same thing, except for we've replaced all of our hydrogens with chlorines. It doesn't change the identity of the acid. It's still going to be an oxo-acid. But now we've got this extra electronegativity, more electron withdrawn groups. So if we compare these two in terms of acidity, the one with the chlorines, you know, structurally they're the same, except for one's got chlorines. The one with chlorines is going to be more acidic because we've got that electronegativity, which is going to make this oxygen-hydrogen bond weaker. Anyhow, both of these are oxo-acids. We should be comfortable drawing Lewis structures.
Wait, we said which one was stronger?
Ooh.
It would be the Cl, right? Because it's more electronegative?
Yes. Okay. The one with the chlorines is going to have more electronegativity. That electronegativity is going to pull the electron cloud over this way. It's going to make it easier for the hydrogen to leave. That means it's more acidic. Your shock made me want to explain that again.
Yeah, because I thought like the hydrogen got dragged over too, you know, so it'd be like less.
It's not the hydrogen getting dragged over, it's the electrons around the hydrogen, right? And so what we want to think about is essentially the closer this is to being an H+, the easier it is to fall off. So if we are stealing the electrons so that the electrons are pretty much all the way over here, and there's just a little bit of electron density over on that H+, it has a much easier time becoming an H+, becoming acidic.
Yeah.
Cool.
Yeah,
Okay. Good. These we should also be able to draw the Lewis structures. So this for the oxo-acids. Ooh, I didn't give myself enough space. Let's do this. It really doesn't matter which ones you make single bonds or double bonds because we also have resonance structure. You don't need that for this class. That's from 127. But in this case, we've got the same number of oxygens, same number of hydrogens, so the ratio comparison is the same. The only difference is, oh, I made the same thing twice. Let's make that one just a sulfur. The main difference here is I've got sulfur versus selenium. So all things being equal in terms of number of oxygens compared to number of hydrogens, for oxo-acids, I'm going to care about the thing in the middle. What are the oxygens attached to? In this case, what's more electronegative, sulfur or selenium?
Sulfur.
Sulfur, which is not surprising because we know sulfuric acid's a strong acid, and we've never called selenic acid a strong acid.
Okay.
Good on that?
Yeah, so when you said, like, are we comfortable drawing Lewis structures, is that something that we might, it's more like beneficial to us on the exam?
Yes, and it's going to come up more and more often as we get further into the material.
Okay, so it's not like you're going to get us one of these and be like, draw the Lewis structure.
No, you should do that. I want to do that.
You want to draw Lewis structures?
Yeah.
Okay. We'll have all Lewis structures. The midterm will just be all Lewis structures. No. Yeah, there could be places where Lewis structures are beneficial to draw, but I don't think I'm going to ask you to explicitly draw a Lewis structure for credit. Disappointing, I know.
Real quick.
Yeah.
That's kind of mirrored.
Oh.
So I don't
Is it
know
all
if that's an
backwards?
issue.
I have
You
no
can
idea.
still
either.
tell what's going on.
But you can't read
You can tell what's
anything.
going on, but it's completely mirrored.
Why is it mirrored?
I don't know if that's a setting that you can adjust with the webcam, or
No, you can't. I can't read that. Oh, it's not backwards on the screen.
Okay.
And you can't see the whole board. That should help. Okay, let's get more problems.
All right. I have a problem that I wanted to know how to do.
Yeah.
And it is, how much chromate is left in solution when I mix 100 milliliters of 0.22 molar calcium nitrate with 100 milliliters of 0.14 molar sodium chromate.
That's very well.
Thanks.
Perfect. So let's go ahead. Let's start. Oh, that's still not getting the whole board. There we go. Yeah, you don't need to see me. That's fine. So let's go ahead and think about what tells us what we're doing in the problem first. How much? What is how much going to tell us to do?
Stoichiometry.
Right. That means we're going to be doing some stoichiometry. Chances are, was there the phrase at equilibrium anywhere in there?
Just left in solution.
So this is probably going to be at equilibrium, right?
Yeah.
Whenever we're looking at something left over, there's the chance that the equilibrium step doesn't matter, but let's find out. So we're going to start by doing stoichiometry. We're looking for chromate. That gives us a couple good clues. Do we have any KSPs or anything given?
It gives us the KSP for calcium chromate,
That's another good clue.
which is 1.1 e to the negative 8. So,
For calcium.
Yeah, for calcium chromate. Now this gives us two clues. The fact that we're given a KSP tells us there's probably going to be a solid someplace. And the fact that we're given an equilibrium constant is another hint to the fact that we might have to do equilibrium.
yeah.
Always the chance that I'm being a jerk and giving you useless information. I try not to do that too often, right? I try not to put misleading information. The place where you got to watch out for that is sometimes in the free response problems, I'll give you information on the first part that is useful for later parts, but maybe not in the first part. And I don't do that on purpose. It's just like when I give you the first part, I give you all of the important information. but then you need it later. So
You'll
you just gotta
use
watch
it
out
for
for
like B, but not for A.
Yeah.
Is that what you mean? Okay.
Yeah, and that's just because otherwise I forget to put it. Let's all scoot in a bit more. Let's make some space. So we're looking at this problem. Is this off of the homework? Is this problem?
It's off
in
of
your
like
homework?
one of your old worksheets.
Okay, so this is off of one of the old worksheets, like worksheet 2, I'm guessing.
Worksheet 1.
Okay, so this is off of worksheet 1. We're going to start by doing stoichiometry,
Yeah.
right?
So
We notice we're doing how much?
when you convert like to the ions that you need, I like don't know what to do because like in my notebook, I think when you did it in class, you just did like 0.22 like big M and then started like converting, but I always think of it as like it's moles over liters, right?
Yeah.
So how does that work? Because
So
you started with like 0.22 M over 100 milliliters. You know,
when did I do that?
it was for a problem about like calcium oxalate. You were introducing
Okay,
how much.
interesting.
And I also don't know when you're converting to your ions if you use 0.1 liters or 0.2 liters.
Okay, right. So I think I know where you're confused, and I think I know how to deal with it. So we have to think about this. I'm going to erase this and redo it now. So we have to think about this in terms of the 2 steps. We have to think about it in terms of the first part and the second part. So if we're just doing step 1, looking at the stoich, we want to think about this just like we would think about a problem in 127. You can think about it in terms of the calcium nitrate plus the sodium chromate going to calcium chromate plus sodium nitrate. I don't care that the sodium nitrate's crushed in the corner there because we don't really care about it. I do need to fix one thing though. Calcium has a +2 charge, so I'd need 2 nitrates there. Otherwise, my reaction is impossible to balance. I should, of course, anytime I write down an equation, also put aqueous, solid, aqueous. But again, I don't care about that last one. Now, when I'm looking at this in terms of stoichiometry, because I think I know where you're talking about the 0.22 over 0.1, and that's in the second step, not in the first.
Oh.
So in the first step, we're just looking at the fact that we have reaction. So we're going to be doing all of this in terms of moles. So I'm going to start, and I'm just going to say, how do I convert this amount of calcium nitrate to a number of moles? I'm going to have 0.1 liters times 0.22 molarity. How do I convert this amount of sodium chromate into moles? I'm going to have 0.1 liters times 0.14. And you can think about it if you like moles per liter. I can do this. Moles per liter. Right? Liters will cancel out. I'll be left with just moles. And that's where I'll start my stoichiometry, is when I've just got the moles. I can do 0.1 times I can do both of these in my head. Oh, good. And that's going to give me 0.022 moles of calcium nitrate. The important thing there being the calcium. And I'm going to get 0.014 moles of sodium chromate. The important thing there being the chromate. Starting with 0 calcium chromate, and I don't even care about the sodium nitrate. That's all just spectator. Reaction step. We're going to recognize limiting reactant is obviously the sodium chromate. Because it's a 1-to-1 ratio, I can just pick the smaller number. Also, we have a hint to this in the question. The fact that I'm asking how much chromate's left over. If chromate was the excess reactant, you wouldn't have to do an ice table. The problem would just be stoichiometry. And that would be boring. We want to do the ice table too. So we'll go ahead, we'll do our reaction step, minus 0.14. I'm still going to put in the mole ratios, even though they're just multiplied by 1, because we should always remember our mole ratios. Yes. The coefficient of the limiting reactants on bottom for each of those. And then we've got how much excess do we have left over? 0, because it's our limiting reactant. We make a whole bunch being relative, we make a whole bunch of calcium chromate, and we just have a little calcium nitrate left over. Math in my head. 0.08. Double check. Okay, great. 0.008. Yeah, there we go. And we're going to need a couple things here to do the next part. Right? I'm going to need this 0.008 for the next part. So right now, at this point, we've just done our stoichiometry.
So you don't take into account that you're combining two different solutions at this point because, like, can you explain how you, like, differentiate between when you, like, need to combine your solutions and it changes your concentration? Because I know that at equilibrium, like, then you have to worry about it because they're both being combined. But at this point, like, why don't you?
Right. So that's a great question. That comes up quite a bit of, like, when do we switch to concentrations? When don't we switch to concentrations? So when we're doing stoichiometry, if I ask, right, and it really has to do with the difference in what we're asking for, right? If I ask, what's the concentration of calcium at the end of the reaction step, then we'd have to convert this moles to molarity, and we'd want to do it for the total volume, right? When we're doing this start, it's like you've got two separate test tubes. When I mix them together, and I'm doing it for moles, so when I mix them together, the volume doesn't matter because the number of moles is set regardless of the volume. But when we go to step 2 and we're doing equilibrium, then we need to know the concentrations, and that's where the total volume matters.
Okay, so it doesn't matter here because you're only finding moles and that doesn't change, but the volume of, like, the solution is what will change and the concentration changes. Okay. So
let's go ahead and get to step 2. I'm going to leave those things in the green boxes. Help me remember what they are, because they are going to be the things that I put into my initial step for my equilibrium. So step 2, I'm going to do my equilibrium, right? I had over here one of the things I erased. I had 0 moles of chromate left over. We look at that, we say, okay, clearly I can't actually have a 0, otherwise I'd never be at equilibrium. So I have to think about what happens for essentially a correction to the stoichiometry we've done, the equilibrium that happens. So I'm going to look at the calcium chromate, solid, redissolving into calcium 2 plus CO4 2 minus, aqueous. And this is part of where we need to use that total volume. So we know that our chromate very easily has 0 molarity left over. I got my 0. I can erase that now. I've got it figured out.
And then the 0.008 is divided by 0.2 liters.
Yes, right? Because at the end of that reaction, when we had our excess, we have our 0.008 moles. We have our 0.2 liters. That gets us to the concentration. At this point, I've taken my 2 separate test tubes. I've mixed them together. And when I find my concentration of calcium, I have to do it for that total volume. That'll take care of that one. I'm going to put it in parentheses because we're not really going to care about it for this point, but I'm also going to have that 0.014 moles of solid that I don't really care about. This problem is not asking about the redissolve step at all. It's there. Solid doesn't influence the equilibrium, but I just wanted to put it there so I fix that. So we can go ahead and look at this. We're going to have our initial concentrations of don't care. Oh boy, calculators help.
It's 0.04 molarity.
Oh, that makes sense. And 0 molarity. I can do my change. Again, we almost always skip this step just in our head at this point. Since we've got 0 concentration here, we know the equilibrium has to go this way because our Q is equal to 0. If we had both things present, we'd have to do a Q versus KSP, but we've got a 0. So we know that the change is going to be plus X plus X. This one's nice. Everything's a 1-to-1 ratio. I've got my equilibrium. The equilibrium here is going to be 0.04 plus X and X. With a KSP of 1.1 times 10 to the minus 8, can we use the x is small approximation? Comparing this value to that value? Yeah, probably. So we're going to go ahead and just say that's small. And we've got something that's relatively manageable of 1.1 times 10 to the minus 8 is equal to 0.04x. Can you solve for x? I cannot. In my head. I need your help again.
It's 2.75 e to the negative 7 m.
That x is our chromate left in solution at equilibrium after the reactions happened.
So
Okay, concentration wise.
Yeah. Since this was all in the ice table, we do it all in terms of concentration. Question?
So if we were to do like a Q versus KSP, could you show me an example of what that would look like just for this problem?
Yeah, so if we wanted to do a Q versus KSP, remember Q is defined by the initial conditions. KSP is defined by the equilibrium conditions. Now we have our KSP given to us. It's 1.1 times 10 to the minus 8. We'd have to calculate our Q. And remember, it's got the same expression, but different numerical values. So I would just 0 times 0.04. What's 0 times 0.04? Just 0. Right, and this is the situation. The reason we've skipped this so often is because we've almost always had problems where one of our concentrations is 0. And then we can do our comparison. KSP is greater than Q, because Q is 0. If KSP is greater than Q, we know we're going to be making more products.
Okay. And then also, can you explain again conceptually why you do the redissolve and how it can't be 0 equilibrium?
Right. Okay. So again, when we write down our initial here, we've got our Q versus KSP. We know that this 0 is not at equilibrium. Even though the KSP is really small, right, 10 to the minus 8, this thing still needs to have some chromate in solution in order to be at equilibrium. There needs to be at least a little bit. So essentially, the reason we do this in 2 steps is because the stoichiometry step essentially overestimates how much solid is formed. But if we tried to do it all at once, you'd essentially be trying to do a relatively complicated. You wouldn't be able to use the x is small approximation. You'd have all kinds of issues, number of significant figures. You have to keep 8, 10 significant figures, and you wouldn't be able to use x is small. Breaking it into 2 steps is not naturally realistic, right? Nature does not make too much precipitate and then break apart. But it's much more easily to do mathematically.
Okay.
In terms of the redissolve, we could kind of just compare this number to this number. We'd have to multiply by 0.2 to get our molarity into moles so that they're both in moles. But we can tell this is way small compared to this. So the redissolve is not significant in terms of the amount of solid we made, but it matters for how much chromate is in solution at the end of the reaction. Yeah.
I mean, the redissolve would take the calcium ion into account too, right? Not just the anion. So you wouldn't just compare X to 0.014. It'd be like X and 0.4, right?
Well, so this would be, the 0.4 would be essentially increased by the redissolve.
Oh, yeah.
Right? And this would be reduced by the redissolve. And again, because it's 0.04, the x is small approximation tells us, oh yeah, it's not going to change the calcium concentration either.
Okay.
But yeah, we do need to think about it in both spots. We just kind of already thought about it here.
So if you were to ask us, like, how much solid redissolves, we just take 0.014 and subtract x.
Ooh. So let's be careful about this. Where did this 0.04 come from?
The stoichiometry step.
Yeah, this was the excess. This calcium that's in solution has nothing to do with the solid, right? That's the excess left over. it's only this plus X, this amount that falls apart from the calcium solid we formed, that really matters for the redissolve. It's the X that matters.
Yeah.
Cool. Okay. Any other questions on this problem?
Would X like be considered molar solubility of the solid, kind of?
Yes, in this solution with a common ion effect, right? Because this is how much solid dissolves if there's this concentration of calcium ions. Yes, it would
Okay,
be.
but if there was like nothing, then of course X would be
Molar
a
solubility.
lot bigger.
Yeah. Yeah, it would be a lot bigger. It'd be like on the order of 10 to the minus 4.
Okay.
Quick question, just based off of the KSP and Q. I thought it was KEQ versus Q.
KEQ versus Q. Keep in mind, technically, yes, KEQ versus Q, but remember, KEQ is kind of an umbrella term that can refer to KSP, KA, KB, KW, K reaction.
I just had a weird note somewhere where it was, okay.
Yeah. So KEQ is just generic equilibrium constant for any situation.
Okay.
Other questions on this one? Great. Let's get another one going. Who else has a question?
I had a question on 9 from the homework.
Yeah, what's number 9?
So 9 was talking about an aqueous solution of hydrogen sulfide, and it contains H2S, HS minus, S2 minus, H3O plus, OH minus, and H2O. And my question was about C, which asked about placing only H2S in water, and then you're supposed to rank like the increasing concentrations of what would be present.
Okay. So essentially this is qualitative, right? I didn't give you KAs or anything like that, right? So we can think about a couple things. Is H2S an acid?
Yes.
Yes. So the first thing we can say is that H2S is going to break down into H3O plus HS minus. That's going to happen. Is HS an acid?
Yeah. So
Yeah. So we can also say HS minus is going to break down into H3O plus S2 minus. And what we really have to think about is how likely is each of these things to happen, right? And it's tough to tell without Ka values, but we can do some logic from some of the other things we've learned. Is H2S a strong acid or a weak acid? So since it's a weak acid, we know that this is going to happen to some extent, right? This thing is going to fall apart. We are going to have some H2S form. We're going to have some H3O plus and some HS form. What's the assumption we make with weak acids? Water has no effect. And there's a second thing.
The amount that redissolves is small in comparison to the original amount.
Yes, but not redissolves, the amount that just dissolves, right?
Yeah.
The phrase that we typically use is the amount that the acid disassociates is small. So that essentially means our initial concentration of H2S is going to be about whatever we put in it, right? We're going to make just a little bit of H3O plus and just a little bit of HS minus from that. Just a little bit, right? This thing's going to have something on some Ka value like 10 to the minus 7, 10 to the minus 8. We're just going to make a little of each of those. Then we think about this one. Is the second proton falling off easier or harder? Harder. So that means, yeah, this could happen some, but it's going to happen like even less than the first reaction, right? So if I wanted to look at my ratios, my concentration of each thing, the H2S would be the most, the HS minus, well, water would be the most, of course, right? We shouldn't even consider water in that list, right? Because there's water everywhere. But the H2S would be the most, the HS minus would be next, and probably close to the H3O plus. And then the HS minus falling apart would barely produce any S2 minus and any H3O plus. Technically, if you remember, does S2 minus like to exist in water? No. This thing actually almost entirely lies that direction. You would probably make a very, 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 very small amount, if any, of this S2 minus. So just the logic thinking there. We could also completely do this with numbers, right? We could look up the Ka of H2S and the Ka2 and actually do the ice table for each one. But I think you'll get the same thing that we got qualitatively in terms of relative amounts. And that was problem 9 from homework 3?
Yeah.
Okay.
So when it is asking about, like, it says if the solution was prepared by placing only H2S in water and then put the species present in order of increasing concentration, like, do you assume both steps because HS minus could technically still donate a proton, or?
It could technically still donate a proton, but what we're going to find if we look at the Ka values, its amount of donation is going to be negligible.
Yeah.
Right? It's really not going to do it.
But how do we know then to do, like, these 2 steps if you gave us another acid? Like, do you know that you
Great
have
question.
to do 2 steps if it's going to be, is it a diprotic acid?
Mhm.
And then, like, if there was a triprotic, you do 3 steps.
Mhm.
Like, you always just do as many steps as many protons can be.
Exactly.
Okay.
Right? So we do a step for each proton that could fall off.
Okay.
So we could, if you'd like, we can do a not the problem. I'm going to see. I don't know how to, like, check what people are saying. Why didn't we use the concentration of chromate in our Q? The concentration was 0, so that's an old question. Sorry for people watching live. I'm probably going to do a terrible job answering your questions. I'll try. Let's see what would happen for phosphoric acid. I need to, like, hire somebody to sit and watch the questions that are getting typed up.
I can sit in here.
Great. You don't actually have to, but
Well, the chairs come here.
that chair is comfy. Go for it. Whoever's willing to keep an eye on chat gets to sit in the comfy chair. Not the comfy chair. Sorry. Just wait. Never mind. Monty Python. Let's look at what would happen for H3PO4, right? So in this case, we'd be looking at 3 steps. We'd look at H3PO4 going to H2PO4 minus plus some H3O plus. We'd look at H2PO4 minus going to HPO4 minus plus H3O plus. And we'd be looking at HPO4 2 minus going to PO4 3 minus plus H3O plus. And again, we kind of see the same type of thing happen, right? For each step, we're going to assume this one's going to disassociate, but not that much. We're going to use the X small approximation. So this is going to have, like, all of it left, and we'll make some of that and some of that. Pretend like the length of the line gives us a sense of how much there is. Then this amount actually falls apart a little bit and a little bit. And then this amount falls apart just a smidge and just a smidge.
It's 2 negative on the HPO.
Yes. 2 minus on that HPO4. So we should have mostly H3PO4 left over. Some of those. And then our H2PO4 is going to fall apart to some degree. The chances that our HPO4 2 minus falls apart, probably very little. Right, and again, we can get a sense of how much if we looked up the actual Ka values for each of these. If we had the Ka value for this, we'd find out that this one actually falls apart pretty well. H3PO4 is a pretty good weak acid. H2PO4 might actually end up with a little, I think it's still going to be this order. I think you'll still have mostly H3PO4 because the H2PO4 you make also falls apart some, right? But we could be, like, just from a qualitative standpoint, this is the order I would think. This one's most. I think because we've got 2 sources of H3O plus, it would be more than the H2PO4, and then the H2PO4, and then the HPO4 and the PO4 3 minus would be 3rd and 4th. We could get technical with this, right? We could be quantitative and actually give you the Ka values and some initial concentration of this and make you do 3 ice tables where each one leads into the next. But we didn't do that. We're just looking at the qualitative. Good?
Yeah, I think that makes sense. I'm just a little confused on where you're saying like there would be more H2PO4 minus than H3O plus because.
No, I think there's going to be more H3O plus
okay.
because I've got 2 places where I'm producing H3O plus and only 1 place where I'm making H2PO4.
Okay.
Yeah.
If you're given like the initial concentration and the Ka values for each one, how do you find the pH of the solution?
Ooh. So like you put H3PO4 into solution, you have the Kas for each one, you got to do like a chain. You would have to do the equilibrium and leave the equilibrium into each other and then total your Ka values. It's an interesting question. Should we do it?
If you're considering putting it on the midterm.
I wasn't considering it until now.
Yeah, I know.
So let's go ahead and see. We're pretty good at dealing with, and this is the exact kind of thinking we want to have. I'm going to do it for. We haven't really talked about polyprotic acids. So honestly, I don't think it'd be fair for the midterm because we haven't talked specifically about polyprotic acids yet. But we can look at it still.
You did give an example in class. You use sodium, hydrogen, and sulfur, and then you give 2 Ka values, and you say calculate the pH.
Yeah, that one. But in that problem, that was the example on the screen. You'll notice one of the Ka values is so small you don't need to consider it. Right. The Ka2 for HS minus is so small, it's not going to have an effect. So let's hold off on doing a polyprotic acid calculation until we get past the midterm and then we actually talk about polyprotic acids. Another question.
Sorry, go ahead.
Okay. It was, I know where it is, homework 3, number 17. Sodium benzoate has, let's see, it's a food preservative. And you calculate the pH of it in a 0.5 molar solution. Yeah. So basically the way I thought about it was like it dissociates into sodium and then the benzoate ion, right? But so then, since it's just in water, I don't know, like is it going to react with like auto-ionized molecules in water?
Hold on, you said 17, right?
Yeah.
So if it's sodium benzoate, why does it say that on our homework?
Let's see. Sodium benzoate is used to calculate the pH of the sodium benzoate solution. That's the chemical formula for sodium benzoate.
Okay, so we could just go to this though?
Yeah, so it turns out that, and I wrote benzoate on the board before. Benzoate is technically a benzene ring. That's benzoate, right? Got a benzene ring with a carboxylic acid attached to it.
So then benzoic acid would be COOH.
It would be a COOH. It would be a
Weak acid.
Which is also which category of acid?
An oxo-acid.
Yeah, it'd be an oxo-acid. So when we look at this, we could hypothetically, theoretically, technically look at this in 2 steps, right? We've got sodium benzoate that's going to disassociate through a solubility reaction, but it's a sodium compound. So we're just going to assume that it completely falls apart, right? And the thing that we actually care about is the sodium ion going to interact with water in any substantial way?
I don't think so.
No. What about the benzoate anion?
Yeah, it will.
Yeah. So the part that we actually care about is here. The Bz minus reacting with H2O liquid. The benzoate anion, which is this thing, acting like a weak base, being a proton acceptor, with water being a proton donor. Forming HBz minus plus OH. That's enough.
Why did we put 0.5 as the concentration for all 3?
So when this falls apart,
Mhm.
It falls apart to 0.5 molarity sodium and 0.5 molarity benzoate. Right? Because every sodium benzoate falls apart to an equal amount of sodium and benzoate.
Oh, because of sodium solubility?
Yeah, right. We assume 100%. We're assuming that it's 100% soluble because it's a sodium compound. If we looked up the solubility of sodium benzoate, it's probably 30 or 40 grams per 100 milliliters. Concentration is way higher than 0.5. So this is probably going to completely dissolve. Yeah.
Are we assuming, so sodium and water don't have an important interaction because it forms a strong base and so it'll completely redissolve?
Yeah, and I should be more careful with my words because sodium and water are definitely going to interact.
Yeah.
They're going to have ion dipole interactions. However, there's not going to be any reaction because of that interaction. Whereas with the benzoate anion, because it can act like a proton acceptor, we're actually going to have a reaction of benzoate with water.
And it doesn't form a strong acid, so it will affect the pH.
Correct.
Okay.
Because we're forming a weak acid, we affect the pH changes, right? We've got the conjugate base of a weak acid. That's come up a couple times. Conjugate base of a weak acid. So if I'm trying to find the pH, what are the clues here of what's going on? Whenever we say pH, that tells us
The negative log of the hydrogen concentration.
yes, the negative log of the hydrogen concentration at equilibrium. Yes, that's the important part. Whenever we're talking about pH, we're almost always talking about an equilibrium phenomenon. So we can look at this and say, okay, what kind of table should I do for this then? Ice table, perfect. We're going to set up our ice table. Because of this 1-to-1 ratio and the fact that the sodium benzoate completely falls apart, I'll start with the 0.5 molarity here. I'm not going to care about water. I'm going to say I start with 0 benzoic acid and 0 hydroxide. Now, we know the 0 benzoic acid and the 0 hydroxides are wrong, which is why we're doing the ice table. We've got to fix it for our equilibrium values. Can you solve this ice table?
Well,
Do we have the Ka for benzoic acid? We'll have to get the Ka for benzoic acid. I have it right here. Ka for benzoic acid is equal to 6.3 times 10 to the minus 5.
Or is it the same thing since aren't we dealing with a weak base here?
Yes. So what do we need when we do our ice table of minus x plus x plus x? Approximately 0.5 x in x.
Do we need to like get the KB, so like Ka times?
Exactly. So with what we've got set up, with the reaction that's happening, we've got Kb equals x squared over 0.5. Again, using the x is small approximation over here. I need an abbreviation for x is small. XSS doesn't work.
I just do XIS.
XIS, that makes more sense. X is small there. Notice we need the Kb. How do we get the Kb?
Kw minus Ka.
No, there we go, yeah. I know you knew what you were saying.
Yeah.
But Kw divided by Ka. So we can just plug that in. I can write down Kw divided by Ka equals x squared over 0.5. I can plug in my Kw and Ka values. 1 times 10 to the minus 14. 6.3 times 10 to the minus 5. And y'all can solve x for me, hopefully. Because I can't, it's not in my head.
It's 1.58 e to the negative 10.
1.58 times 10 to the minus 10.
I got 8.89 times 10 to the negative 6.
Oh, yeah, 10 to the minus 10. Did you forget the square root?
Oh, we're solving for x completely?
Yeah.
Oh, I just did the KB. So
Oh, that's the KB. We're going to take that KB, we're going to multiply by 0.5. Then we're going to take the square root, and we get?
I got 8.89 times 10 to the negative 6.
Yeah.
8.89 times 10 to the minus 6. Agreement? I got 3 people agreeing. I'll go with it. What is X?
X is the concentration of benzoic acid and OH.
Yeah, so it is the concentration of the benzoic acid at equilibrium, but more importantly, for calculating pH, it's our OH minus concentration at equilibrium. We can use the OH minus to find the POH, and then we convert to pH. Yeah. I have no idea what the final answer will be.
But
Can't
it's
do
like
math in my head.
pretty
But
easy for me.
at that point, we should have a relatively easy time just doing those manipulations. I will say this, though. There's 2 ways that you can do the manipulation, right? You could switch to OH minus to POH and then do the minus 14. You can also recognize the fact that 1 times 10 to the minus 14 kW is equal to H3O plus times OH minus. So you could just convert that OH minus to H3O plus and then do negative log of it.
So wait, the X that you just calculated is the concentration of OH minus, right?
At equilibrium.
Okay.
So benzoic acid is a weak acid, right?
Yep.
So it'll partially dissociate.
Yep.
Right. So but we're just assuming that it all sticks together as HBZ for the purpose of this problem.
No. How much sticks together?
Some of it.
Only some of it. And actually only a small amount of it, right? Only 8.8 times 10 to the minus 6, 8.9 times 10 to the minus 6 moles per liter is actually sticking together.
Yeah.
And the reason we've got so little sticking together is because we've got this higher concentration of benzoate anion sticking around.
Okay. Yeah, that makes sense.
Cool.
Trying to find a calculator that works.
I have one in my
that
bag right
works.
there, but this one's funky.
Is that one funky?
Yeah.
Is it one of the business calculators?
Yeah, probably.
Oh, where'd my working calculator go? Oh, here you go. Other questions?
I had a competitive solubility problem.
Oh boy. Okay. What time is it, by the way? Because I've got class at 3 as well.
2:22.
Oh, plenty of time. Great. Competitive solubility.
Is that what we did on quiz 2? Yes.
I can't remember. Yes, that is what we did on quiz 2.
Yeah, we should do that.
Okay, so the problem is silver mining uses competitive precipitation to isolate the silver. So there's, in a mixture, there's silver ions, lead ions, and copper ions. So,
Which kind of lead ions?
I guess Pb2 plus.
And copper ions +1, +2.
It doesn't specify.
Ooh, that's problematic. Let's go with +2. That's more common.
Yeah.
But it could be +1. Those definitely have different solubilities associated with them. Let's go with 2+.
So then it asks which compound we would use to isolate silver and why. So I think that's just like doing a giant.
It doesn't
like,
give you any options?
Well, no, it gives us potassium iodide, sulfuric acid, sodium sulfide, and potassium chromate. So I'm guessing that's just like a big like Google search like fiesta.
Yeah.
And you like search all the KSPs and like compare the differences.
Yeah, so we've got
It's basically just comparing
just
iodide
these 3?
And chromate.
Chromate,
And wait.
sulfate.
Sulfuric acid. Or hang on. Sodium sulfide.
Sodium sulfide.
Yeah.
Okay, great.
So then it'd just be comparing all the anions.
Yeah, so we got a KSP Hunt Fest.
What is this from, homework or worksheets?
Or
Worksheet.
something else.
It's from the solubility worksheet, I think.
Okay. Was it iodide or iodate?
Iodide.
Okay. Great. So iodides. We got copper 1 iodide. We got a no thing for the sulfate. Oh, I might have to web search this to get it all. Chromates. Again, I've got silver and lead chromate. We can tell that we can tell chromate's going to be a bad choice. We can rule some things out. Silver chromate to lead chromate, 2.3 times 10 to the minus 13 versus 2.6 times 10 to the minus 12. I don't have one for copper, but I can tell if these two things are precipitating at the same time, it's not going to do a good job getting the silver alone.
Yeah.
So I can pretty much rule out the chromate. Let's go ahead and see what I've got for iodide. I've got silver and lead, but again, I'm missing copper. And this one might be a good choice. So we might have to do some hunting. 8.3 to 10 to the minus 17 for silver. 7.9 times 10 to the minus 9 for lead. That looks like it's going to do a pretty good job separating.
Yeah. So
we have to keep in mind, this is going to be square root, this is going to be cube root. Because we're going to have a 1-to-1 ratio versus a 2-to-1 ratio, a 1-to-2 ratio.
Yeah.
So we have to be careful about that, but I think that's going to make it separate even better in this case. And I don't have a number for copper. Let's look at sulfate real quick. Silver sulfate versus lead sulfate is 1.5 times 10 to the minus 5. I'm just looking through an old textbook to get these numbers. In the future, I'm probably just going to publish my own list because we're changing textbooks again this summer. Yeah,
lead
doesn't matter to you all, but for me, it's a total headache. 1.6 times 10 to the minus 8 ish.
Mine says 2.53 times 10 to the minus 8.
Close enough. So that one could work, but it's not that great. And again, I'm missing my copper value. Sulfide. Oh boy. Silver sulfide.
Oh, lead sulfide is 3 times 10 to the negative 28.
Silver sulfide. 8 times 10 to the minus 48.
Nice.
And copper 2 sulfide, I actually have a number for this. 8 times 10 to the minus 34.
So there's obviously like the largest separation with that one, but like they're all just so insoluble.
Right. So this one's going to be problematic for a couple reasons. One, I'm going to be taking the cube root of 48 versus the square root of 28 and 34. That's going to, because I'm going to have two silvers for one sulfide. What's 48 divided by 3?
16.
16-ish? I think it's actually just 16. 28 divided by 2 is 14, and 34 divided by 2 is 17. So
are we doing AG a charge of just positive?
Yeah, silver's just a +1 charge. Yeah, almost always. And then the lead, we're assuming +2 on the lead and copper, and we're like, is that right? We don't know. So once I take into account the different mole ratios of ions and the fact that it's cube root, square root, square root, this one's actually not looking that great.
Yeah.
It's also not looking that great because with numbers so small for all of our KSPs, we're likely going to run into very serious excess small approximation difficulties. This makes me really want to find a paper real quick. I tried to clean. Oh, good. I left it right on top. I got this list of solubility constants that I might give out in the future, just so that way we're all using the same source for solubility constants. There were some problems on some of the homework where we were using different KSP values and getting different answers. Copper iodide. I've got a copper 1 iodide, but I don't have a copper 2 iodide. Do me a favor, hop on Google real quick and Google copper 2 iodide and see if it's got a reasonable solubility or not. So we're missing one of our values. It looks like the iodide is going to do the best job separating.
On the midterm, if you were to ask us like which anion would be best to separate out the cations, would you give it to us where they're like all 2+, or would you want us to compare the molar solubilities?
Depends on how mean I'm being. Rather than how mean I'm being, depends on if it's a short multiple choice question or a long multiple choice question.
Okay.
In a short multiple choice question, you can just directly compare I'd probably make it so you could just directly compare the KSPs, right? Just
Okay,
can you figure out what you're supposed to do or not? In a long multiple choice question, I'd probably be like, which one do you do? And you would have to actually calculate the molar solubilities for each.
Okay. I'm getting the Wikipedia page because it came up with a bunch of crap.
Oh, crap. So let's go ahead and operate under the assumption that Ki is going to be the best.
Yeah.
Right? We're going to assume that copper here is either going to be incredibly soluble or hopefully a higher solubility. We're going to say that essentially these two are the things that I have to separate. We're going to pretend for now until we get other information about it. We're going to pretend that that copper 2+ is just with I minus is just going to be soluble. So we look at this and we say, okay, the fact that you're getting junk makes me think that we're not going to have
We're
value.
looking for copper I.
Yeah, CuI2. Do they have it?
They just have CUI.
Okay, so they got the copper one. I'm going to assume CuI2 is just not going to be a factor here.
Okay.
Is that a safe assumption? Again, this problem is somewhat, I don't want to say problematic, but this problem is somewhat problematic because it didn't specify whether we were looking at copper 2+ ions or copper 1+ ions, which those do have different solubilities.
Yeah.
So that's a little irritating. But let's go ahead and say it's got some value that's going to be bigger than the lead. And so the lead, the two that are closest to each other become my limiting factor, right? So I want to theoretically add as much iodate as possible. And the lead gives me my upper limit to how much iodate I can add. So at this point, we're going to kind of neglect the copper and say it's not going to be in the way. And we're going to say, okay, so we're going to saturate the lead 2+ with I-. We're going to find our maximum I-, that is to say our highest concentration of I- that will give the best separation without producing any lead iodate solid. What kind of table? If I'm trying to saturate? Ice table, right? Saturate's another one of those secret words that tells us we're doing an equilibrium. So I'm going to be looking at PbI2, going to Pb2+ plus 2I-. Did we have initial concentrations for this, or was it just pick the best ion?
It was just pick the best ion. And
then we're done.
Well, there's a part 2.
Let's look at part 2.
Yeah.
This is where I need to know part 2, right? Because
yeah, that'll give us an initial concentration.
what do they tell you?
They say with your selection in the previous part, how much of the compound would you use to achieve maximum separation? And then how much of each metal ion would be left in solution at the maximum separation?
This is on a worksheet, isn't it?
Mm-hmm.
Yeah, my worksheets are a little, they need some details. Do me a favor, email me about that problem so I can make it better for future worksheets.
Okay.
You've got on quiz 2, you have a pretty good example that's pretty similar.
Yeah, so quiz 2, which was homework, I think homework problem 4 on homework 2 is the same thing. Let's make up some concentration so we can do this. What's your favorite number?
0.5.
0.5? What's your favorite number?
5.
5? Let's make this one 0.55. Just hang that up. I get junk mail calls all the time. So we're going to say the initial concentrations are 0.5 and 0.55, and that's all we need to do this. That's the only part that was missing.
Of the ion?
Yeah, of the cations, the positively charged ions. right? So in order to do this ice table, in order to maximize my separation, I need to know the initial concentration of my lead here. And I'm going to assume that I've got 0 iodate. And I want to find how much iodate can I add in order to get to saturation. So this is not like our typical solubility table. We really are just trying to force equilibrium by having some x value there. Well, we could call it 2x since it's a 2-to-1 mole ratio, but I really just want the whole 2x. I don't care about the mole ratio because hopefully I'm not making any of this solid. Hopefully it's all aqueous. Right? I don't want any solid. So we look at this and we say, I know the KSP is 7.9 times 10 to the minus 9. That's going to be equal to 0.5 times 2x squared. But again, we're solving for 2x, so I'm just going to divide by 0.5 and take the square root so that we get 2x is equal to, I'm trying to do this in my head, 16 times 10 to the minus 9 would be 4 times 10 to the minus 4.5 would be 8 times 10 to the minus 5?
So can you
I think I'm off. Help.
just walk me through like the conceptual thought behind the like ice table?
Yeah, so essentially this is a little bit misleading, and that's why I'm putting the box around the equilibrium step, is because this is not our typical solubility, right? Normally when we're looking at solubility, we're looking at how much solid falls apart.
Mm-hmm.
Here we're looking at saturation. So I'm trying to make an equilibrium situation where no solid will form, right? Saturation is that point where maximum ions in solution without any solid forming.
Okay.
So imagine, let's solve for that 2x value and see what we get.
7.6.
I don't remember what I said, but I don't think that was it.
So like 8.
Did I really?
Or wait, when you take the square root of that, 2x becomes 1.26 times 10 to the negative 4.
Did you solve for x or 2x?
I think solve for 2x.
Oh wait,
Divide by
I got
2.
1.26 times 10 to the
when you take the square root of it,
Did you forget to take the square root? No, there's 1.26 times 10 to the minus 4. Man, that means I was less right. I liked the other
I
answer.
thought it was a 2 for the KSP. That was 2.9 instead of 7.9.
Oh, yeah, that's 7.9, sorry. That would, I didn't think it'd make that much of a difference, but okay. 1.26 times 10 to the minus 4. This is going to be our molarity of I minus.
so just leave that as 2x. Oh yeah, because that.
Yeah, right. So if I get the concentration of iodine to 1.26 times 10 to the minus 4, let's say 1.25 times 10 to the minus 4. If I do my Q versus KSP, no reaction will happen. If I go to 1.26 times 10 to the minus 4, Q equals KSP. That's at equilibrium. If I go any further past it, if I go to 1.261 times 10 to the minus 4, reaction happens in solid forms. So the number I found here is the saturation point of lead, of iodide at this lead concentration.
So this means you would add, like if you just had a vat of like mining slurry, right?
Uh-huh.
And you dump that amount of iodine into it.
Yep.
Like silver would form, right?
Would
And
crash
then
out as silver iodide.
if you added any more lead,
Silver iodide.
like or silver iodide, lead iodide would start to form too,
Yeah.
and that's what you know.
And then our silver and our lead would be mixed up in the slurry that we're trying to get. And we'd be like, oh, we're ruined.
Wait, so would you need to find how Ag or how silver and iodide precipitates, like how much iodide it would take, and then would you add that?
No, this depends on what the question is asking, right? And the question just asked concentration for maximum separation. That's the concentration, right? I could have also done the more challenging question of how much iodide is necessary to precipitate all your silver and then saturate.
Maximum like separation.
Right. Yeah.
So for maximum separation, would you take into account how much you would need to separate the silver, and then like do as much as you can to get the lead iodide?
Yeah.
So you would add the.
You would add those. If I was asking how much iodide you were asking, right? If I was asking for a number of moles of iodide you added, you would have to do that. You'd have to do the extra step. If I'm just asking for the concentration that maximizes separation, you're just worried about the concentration.
Okay.
Right? Question.
We have a question. How is the 2x concentration related to the concept of saturation?
So here, remember the whole reason we set up this 2x thing is, again, whenever we're looking at precipitation, we want our x value to be our molar solubility, right? So we have it as x is the lead iodide that would fall apart. But in this situation, we just want the concentration of iodide at equilibrium. So if you solve for x, you would then have to double it so you can get the concentration of I minus at equilibrium. I hope that clears it out. So this is our concentration that would maximize separation. We know at this point, if this is our value of iodide, how much lead is left in solution?
Yeah, that's the next part it asks, is how much of the cations are left in solution at the saturation point.
So
you need 2 more ice tables?
no, because how much lead is left in solution?
0.5 molar.
Yeah, since we saturated without precipitating any of the lead, we've established equilibrium with the lead already.
Okay.
Right? So our lead concentration should not change.
So then the real question is like how much
Silver is
still left.
Yeah, and that's the tricky one. So that's where we have to do another ice table, right? So we should have formed all of our silver into silver iodide solid, which is fantastic because then we could scrape out that solid and now we're rich. Right? We've got silver. Just add some electricity to, you all know electricity because you took 128. You can do the electrolysis of the silver iodide to make silver plating. And then you've got silver out of solution.
Yeah. I think silver is not as expensive as it used to be. Interesting side note. Yeah.
Yeah. Well, I don't pay attention to the precious metals market. So, I don't know. How's gold doing? I don't really care. I don't own stock in gold or silver or anything like that. So silver's gonna fall apart to Ag plus I minus. We know that if we precipitated all of our silver, what concentration of silver do we have left in solution?
0.
0.
How do we know that we precipitated all of it?
Because it's the least soluble one, right?
So you're just like saying that?
Yeah, if we got to this concentration, all of the silver had to precipitate, and then we had to keep adding iodide to get to this concentration.
Oh, okay.
Right? If we got to this concentration, all the silver has to precipitate before we can get to this concentration because it's so insoluble. And this number that we solved for is our iodide concentration. Don't care about the solid. Plus x, approximately x. Can we use x as small? Like that iodide concentration is pretty small. Can we use x as small?
It depends on what. Oh yeah, we can use it.
Why can we use it? Somebody else. 1.26 times 10 to the minus 4 looks like a small number to me. What do I compare it to say I can use the x small approximation?
The KSP of
the KSP, 8.3 times 10 to the minus 17. I can probably x is small here. So I'll just leave that as 1.26 times 10 to the minus 4. And then we'll solve. Whoops, 1 is not 8. 8.3 times 10 to the minus 17 is going to be equal to 1.26 times 10 to the minus, trying to write too fast. And sorry, that is sideways. 1.26 times 10 to the minus 4x. You divide by 1.26 times 10 to the minus 4. You get x is equal to 7.9 times 10 to the minus 13. Am I even close?
6.59 times 10 to the minus 13.
Oh, 6.9.
6.59.
6.859?
6.59.
6.59. And that is our Ag plus concentration. So notice we've done a fantastic job separating our solutions. Our silver and lead started out at almost the same concentration. And after we've gotten to equilibrium, our silver concentration is pretty much 0 because it's all been precipitated. And our lead is all left in solution. If we're running a mining operation, we take this lead solution and we dump it into the river. And then we take our silver solution and we turn it into precious metal. And that's why it's really dangerous to play around silver mines.
Yeah.
Moral of the story.
Moral of the story, EPA is probably important, but I don't make policies.
We have a question.
Yeah.
If we can't use X is small, how would we solve the problem?
Oh,
With the quadratic formula, right?
But that isn't
Yeah.
something you're going to ask us.
Right,
It would
so-
basically be like, if X is small fails, like just prove it.
right. So if we're in a situation where the X is small fails, we get to this and we find out that our concentration is about the same as this concentration we started with. We're like, X is small totally fails. In that situation, you would solve the quadratic. You can't use any approximation. I'm not going to give you a situation where you have to solve the quadratic, but I could give you a situation where I ask you, is the X is small approximation good or bad? If it's bad, what would you do? And I'm not saying do it, I'm saying what would you do? So if it's bad, you just say solve the quadratic or the cubic or the whatever.
Yeah.
Quaternary equation, whatever equation you end up with.
Would you ever ask how much solid forms in this situation, like how much silver iodide forms?
I could if I gave you a volume, but it's a pretty straightforward question, right? Because all you do is molarity times volume gives you the number of moles, which is the amount solid formed.
So you'd start with the Stoic table.
You just start, yeah, you do a Stoic table.
Oh, because it's a 1-to-1 ratio and
Yeah.
like all of the silver.
Yeah, you would just do stoichiometry at the start and you precipitate all of it.
I was kind of confused, and then there are 2 more questions.
Sure.
I was kind of confused with when we say how much. I just guess I thought that was always like in moles, but we just start with the Stoic table and then we find the how much in a concentration with the following ice table. Is that true?
For which one?
That's not this one. That was the one that we were working on earlier.
Okay.
So where was it? It's here. When you said how much, we ended up doing the Stoic table and then going on to use an ice table. And that's when you said that we got the answer when we found X, the concentration of chromium at the bottom. So that's what.
Oh, yeah.
For with
So
how much?
technically, so the previous question we did, which is this one, I don't know if you can see that.
Yeah.
Previous question. It asks how much, but it doesn't ask, it says how much left in solution. So technically, without me being specific, you could have put your answer in moles or molarity and either would have been acceptable.
Okay.
How much generally suggests moles, and that's why we did the stoichiometry first.
Okay.
But how much left in solution suggests a molarity for the final answer, which is moles per liter.
Okay. And then there's a question on here. Does anyone know what the special question is that will be asked on the midterm?
No, we haven't hit on that yet. No one's asked it
So
yet.
should we keep just like?
Let's keep going. How much time
Should
do we
I
have
go
left?
through every homework question?
Well, if we don't get to it when there's like 10 minutes left, I'll do it.
We're at 12 minutes.
Oh, jeez. Question.
Yeah, I had a quick one. So for this last problem, we compared the X iodide concentration to KSP for silver iodide,
Uh-huh.
right? I know sometimes we compare to the initial concentration. How do you know when to compare?
So when we're comparing it to the initial concentration so we compared it to this to get a hunch as to whether the X is small would work or not, right? Then if we wanted to say how good was the X is small, that's where we'd compare this X to the initial concentration to say whether it worked or not.
Oh, okay.
So we pre-compared to see if we have a good hunch as to whether it would work or not.
Yeah.
And then we could have done a check at the end to say if it was good or not.
Okay.
Right? Yeah. Other questions on this?
Good luck, everyone.
Thank you. Okay. No one asked the question. No one's asked the question yet.
Does it have to do with pH?
It does have to do with pH.
Does it have to do with the water contribution, like when you assume that water's contribution is negligible when it fails?
It does, but it's a particular problem inside that. There was a problem like this on the quiz.
Oh.
Hold on. I did.
Is it like when you're finding the pH and you're in acidic conditions?
Yes,
Basic.
that's it.
Yeah.
That's it. So how do we deal with these problems? So this was a problem that a lot of people got wrong on the quiz. Apparently there was a problem with one of the tutors or workshop leaders or something, and we had a problem on the homework that was how much. So this is the midterm. There will be a question like this on the midterm. I'm not going to do the same numbers, but there will be one of these on the midterm for your long multiple choice. So how much H3O plus or OH minus is needed to change pH? That's not how you write pH. And we can think of a bunch of different situations here, right? We can think of going from like 4.66 to 6.54.
Wait, will it ever like cross the threshold of
Yes. We could think of going from 8.90 to 9.94. We could also think about going from 4.66 to 9.94. Right? Each of these has a different situation going on. And we have to think about, we can think about it in terms of like a grid. Are we acidic? Are we basic? Is pH going up? Is pH going down? So if we are in acidic conditions, we're going to do our calculation in terms of H+. Right? In both these situations, we're going to do our calculation in terms of H+. If we're acidic and our pH is going down, we're doing our calculation in terms of H+, and we're adding H+. If we are acidic and our pH is going up, we're going to do our calculation in terms of H+, but then we're going to add OH minus. If we're in basic conditions, we're going to do our calc in terms of OH minus. And again, if our pH is going up, we add OH. And if our pH is going down, we add H+. So we've got 4 different situations that we need to worry about. And then the really interesting one, as you cross, because you're going to switch from acidic to basic conditions. And this helps us start thinking about how we're going to do titrations, which is what we're going to get to after the midterm, is how does adding hydroxide change pH? How does it do it for strong acid situations? How does it do it for weak acid situations? That's the next thing we're getting to. So the mistake that a lot of people make is they see pH going up and they do everything in terms of OH minus. And there's a pretty obvious mistake here. Can you hand me my red pen? I'm gonna do this in red because it is a mistake. Or I'm rather going to explain the common mistake. I'm going to use easy numbers so I can go through it fast. If I have a pH of 4 to a pH of 5, my pH is going up. If I converted this to pOH, it would be a pOH of 10 to a pOH of 9. If I calculated my 4 to 5, this is 10 to the minus 4 to 10 to the minus 5. My delta H plus would be 9 times 10 to the minus 5. If I did the same thing on the POH scale, I would have 10 to the minus 10 to 10 to the minus 9. My change in OH minus would be equal to 9 times 10 to the minus 9. So what we've got here is essentially an equivalent change in pH with different values of what we're adding. That doesn't make sense. Something's wrong here. And essentially, what you have to remember is the switch from pH to POH, pH plus POH equals 14. That's from KW. That's from water's equilibrium. And that means that we have a problem with one of these numbers when we consider the equilibrium of water. It turns out that if you did it in terms of the POH in acidic conditions, your X small approximation fails here. And if you did it in terms of, if you were in basic conditions and did it in terms of pH plus, again, your X small approximation would fail. So this green square up here with this kind of algorithmic memorize which one you do in which conditions, that essentially allows us to always be in situations where the X small approximation will work, right? If we're in acidic conditions, the H plus is always going to be large compared to the KW, compared to water's contribution. So X small is going to work. But the OH minus concentration in that case would always be small and water would be significant. Opposite's true in basic conditions. So let's go ahead and very quickly do C before we run out of time, because that's the type of problem that's going to be on the midterm. When we switch from acidic conditions to basic conditions, we actually have to do this in 2 steps. Again, this is all a trick just so we can neglect the equilibrium of water. We're switching from a situation where it's like water doesn't matter to another situation where water doesn't matter. The contribution from water doesn't matter. So we're actually going to split this into 2 steps. We're going to do 4.66 to 7, and then we're going to do 7 to 9.94. I'm going to do part 1, part 2. Part 1, I can switch. That's a part 1. That's not 0. Part 1, I can do 10 to the minus 4.66 minus 10 to the minus 7. Now, that's going to be my change in H plus, and we can think about this as removing H plus. I'm going to remove that H plus by adding OH minus. Then, and we can get a numerical value for that. I don't know how, we're almost out of time. So then we can think about the next one. Now notice, in basic conditions, I have to switch both of these to POHs. So I'm going to do 14 minus 7. That one's easy, 7. I'm going to put the next one. 14 minus 9.94. 4.06. Oh, thank goodness. 4.06. Then I'm going to go ahead and say 10 to the minus 4.06 minus 10 to the minus 7. It's going to be equal to the change in OH minus.
I don't think I really understood what I meant personally.
By adding OH minus. Now, in both of these situations, my pH is going up. Notice the whole course of this, my pH is going up. So I'm always going to be adding OH minus. I'm doing it in terms of acidic conditions, or in terms of H plus when I'm in my acidic conditions. I'm doing it in terms of OH minus in my basic conditions. But both of them are going to be adding OH minus. One is adding OH minus to remove the H plus, and one is adding OH minus to increase the OH minus. Once I get these numbers, I just add the 2 together to get the total amount. Did anyone calculate these just so we can have an answer? Let's calculate these and get an answer.
For the first part, it's 2.18 times 10 to the 5.
Now, the reason that we can say that this is molarity of OH minus that we need to add, rather than changing H plus, is because the H plus to OH minus is a 1-to-1 ratio. And notice this is also in terms of molarity, right? Or I think I'd like to specify moles per liter in this case. Just so that way we have a clear idea that it is a number of moles that's changing. Depends on what volume we have. For the second one,
8.7 times 10 to the negative 5.
Yeah.
Starburst is gonna be grind. It's gonna be like Sunday night at 11 p.m.
moles per liter, OH minus. Now, to get the final answer, I have to add those two together. Oh, that's going to be 1.98 times 10 to the minus 4. Am I right? 1.1 is 10 to the minus 4 moles per liter OH minus.
And then if you gave us a volume, then we would multiply that by the volume.
Yeah, if I gave you a volume, then you could multiply the volume to get the number of moles. That's all I have to go to class. Questions?
Your lab notebook is really quick.
No, it's past week 3. It's past week 2.
I know, it's for like one of the previous ones that I got wrong.
It's past week 2.
We
can talk about it. No.
Oh, I didn't
Here,
know.
let's go ahead and send this.
Bye. You can only see